afternoon, everyone. My name is Qiang Zhang, and this is one PhD candidate from the Wuhan University. Today, my presentation is about optimized strategy for building of LEOs based on BDS only.
Can you use the microphone?
This is my contents. My presentation can be divided into 5 sections. The first is a simple introduction. The second is about the BDS orbital errors. Third is about the onboard aerial receiver PCV calibration. Fourth is the BDS IGS and MU delay jumps. The last is the country and the future work. This is the corresponding research points about aerial field using BDS. For example, use onboard data to enhance the BDS orbit and local products. Use onboard data to determine aerial orbits. Furthermore, the BDS PCV ionospheric and geo-code multiples can be estimated. But there are some questions. First, how much level of the aerial field using BDS can be achieved? Second, if we add the geo-observation to aerial field, the performance can be improved if not known. And the third is, at this time, the BDS orbital presence is larger. The DBDS or the daily jumps are large, and the impact will be analyzed. As we all know, all the aerial field using BDS are based on the efficiency satellites. So I will give a simple introduction for these satellites. The important is that this satellite's altitude is about 800 kilometers. So the reduced dynamic model is very accurate and the POD task is very easy. The right figures are for the architecture of GNOS, GPS, and BDS receiver. This is the introduction of my POD concepts in my research work. The left and the right table are for the dynamic model and the observation model respectively. The importance is that the atmospheric drag co-effects and the empirical acceleration parameters are estimated as constants every 6 hours. The POD occurrence is separated as just 1 day, 24 hours, or 36 hours. Also, the GBM, GFZ, and WHO has its self BDS, PCO, and PCV, but I use the IGS 1480X as BDS, PCO, and PCV. As the second, I make an orbital difference series of BDS GO between GBM and WM final process orbits. It indicates that the nearly daily constant systematic orbits in along track and cross track, but the radial errors don't show this feature. So I thought modeling the BDS geo-orbital errors and daily constant pairs may be a good choice in aerial POD. This top figure shows the geo targeted by efficiency during 1 day. As an example, we can see that this is not the same as the ground station. In the geo-orbital reference frame, the The zenith varied from 0 degree to 10 degree, and the azimuth varied from 0 degree to 360 degrees. So the GEO's orbital belts can be estimated well. As this BDS GEO phase observation equation, I add 3 extra pyramids, BA, BC, and DR represents the GEO orbital belts in ground track, press track, and radio. And the bottom figure shows the distance errors caused by unit orbital belts in the service error for C4 satellite. In order to verify the BDS GEO orbital estimation method, I conducted 2 experiments as a solution A and B. A excludes all BDS GEO exactly, and the B includes the BDS GEO observation, and the long track, press track orbital belts are calibrated. Let's see the results. The GPS derived orbits were used as the reference. We can see the figure and the table. It can be seen that the orbital presence can be improved obviously. Both the 2 solutions can achieve the centimeters level, but when the GEO orbit errors were calibrated in a long track, the orbital errors can be improved by 1.4 centimeters, and in 3 dimensions, the orbital errors were improved by about 20%. So this method was effective. When the orbit errors were estimated, we add them to the original orbits. So the so-called enhanced orbits were recovered. This figure shows the estimated daily orbit errors. It's different day by day, so there is no regular to represent this. In the right figures, unfortunately, not all the BDS can be reduced, but if we exclude a few records which are larger than 1 meter, the last can be shown that the several decimeters GEO orbit errors can be recovered. Let's see the third, PCV calibration. The LEO in-flight PCV calibration was also conducted. I conducted experiments and estimated PCV maps from GPS and BDS observation regions respectively. The grid space is 5 degrees. As the figure shows, the left and the right of GPS and BDS respectively. As a picture, they show nearly the same distribution, but the BDS PCV is much less than GPS PCV because the GPS observation number is less than GPS. But they show the nearly same distribution. In order to assess the impact of PCV on LEO POD, we conducted 3 solutions. The full sensitivity using BDS at the 3 PCV, they are 0 PCV, BDS PCV, and GPS PCV. So they have 3 canned results. The results show that using GPS and BDS PCV can improve the POD accuracy, especially in the 3 dimensions. When using BDS PCV, the process can be improved by nearly 1 centimeter. We can see that in when we use BDS data, the BDS PCV may be a good choice, but the GTS and BDS PCV are consistent. As the force orbital delay jumps, at this we use the WM precise orbits as reference. The BDS was calculated for each BDS satellite. The top figure, we can see that for GEO, the BDS are about half meters. For IGSO, it's several BC meters, and for MEO, it's several centimeters. But for MEO in the along track, it is about twice times in the other two components. And this table shows the statistics of orbital delay jumps for GEO, IGSO, and MEO. In order to reduce the impact of the orbital delay jumps, there are two methods. One is extend the periodic arc length. That is, we extend the periodic arc length 6 hours in the beginning and ending. The two is we try to fit the BDS origin orbits and extend it. So the solution was separated into 4 types. They are used only 1 day, 24 hours, and 36 hours. The BDS orbits are using original and fitted. Let's see the results. Let's show this table. It shows the 4 solutions with including GEO and including GEO. Just these 2, we can see that when we use the fitting BDS orbits, the orbital precision can be improved to about 5 centimeters. And the 36-hour solution is better than 24 hours fit. But if we use the original BDS orbits, it's only about 10 centimeters. When we respect the GEO, we can see that when we add GEO, the GEO's contribution is little. It's because the PCV was considered. At this time, we can, for area field, use each BDS satellite type. At this time, the only satellite, each BDS satellite used to make area field. As we can see that we get both the process by using GEO, the IGSO and MEO works better. But if we use the IGSO, the area field is the smallest. It's about 10 centimeters. When we use the combination of BDS satellite type, this result shows that if the GEO combined with IGSO and MEO, the process was about 10 centimeters, but if we use IGSO and MEO, 5 centimeters can be achieved. So I think IGSO MEO may be the best choice. It makes the bigger contributor to aerial field. This is the last conclusion. In my previous research, we calibrated the BDS GEO orbital pairs and achieve centimeters coincidence orbits. The PCV was estimated using GPS and BDS is consistent. At last, the BDS current orbital delay jumps were considered. At last, the 5 centimeters orbital precision can be achieved. If we add more BDS satellites observation, more precise BDS orbits, the POD performance will be improved greatly. In the future, I will study on GTS and BDS integration using variation component estimating to determine the width of BDS observations. And last, the integral ambiguity resolution is the good method to enhance the phase observation models. My presentation is all. Thanks for your attention.
Thank you. Is there a very urgent, quick question? No? Thank you for the presentation, and we move on to the third presentation on BEIDO. It's given by Florian Dilsner. Initial orbit determination of third generation BEIDO NEO spacecrafts.